Welcome friends, Igor is here, and in this video we will discover connections between the range of a linear transformation and the column space of its matrix representation. In this lesson we will prove that the range of a linear transformation is isomorphic to the column space of its matrix representation, and we will use this isomorphism to compute the range of one linear transformation. Let's get started. Suppose we have a linear transformation T that goes from a vector space U to a vector space V. We also fix any basis B for U and any basis C for V. This allows us to construct the matrix representation of T relative to the bases B and C. And the claim is that the range of T as a vector space is isomorphic to the column space of the matrix representation. To establish that these vector spaces are isomorphic, we need to construct an invertible linear transformation that goes from the range to the column space. The range of T is a subspace of the codomain V, and the column space of the matrix representation is a subspace of Cm, where M is the dimension of V. Here is an idea of the proof. We already have an isomorphism rho C from the vector space V to the vector space Cm. To establish an isomorphism between the subspaces of these vector spaces, we will consider the restriction of rho C to the subspace of V, which is the range of T. Here is a picture of what is going on here. The big outer square is an illustration of the fundamental theorem of matrix representation through the linear transformation T. In particular, pay attention to the vector representation rho C that goes from the vector space V to Cm. The range of T is a subspace of V, and the column space of the matrix representation is a subspace of Cm. So we are going to consider the restriction of the isomorphism rho C to the range of T, and we will prove that this restriction becomes an isomorphism between the range of T and the null space. To realize this idea, first we need to make sure that the restriction of rho C to the range becomes a function from the range to the column space. In other words, we need to show that applying rho C to any element of the range of T becomes an element of the column space of the matrix representation. To this end, let's take any vector V in the range of T. This means this vector is a value of T, so there must be some input vector U from the domain vector space U such that T applied to the vector U is equal to the vector V. Then we are going to look at the matrix vector product of the matrix representation and coordinatization of the vector U relative to the basis B. We apply the fundamental theorem of matrix representation, and we recall that T of U is equal to V. This says that the vector rho C of V is equal to the matrix vector product of the representation matrix and some other vector. In this case, it is rho B of U. But this matrix vector product is a linear combination of the columns of the matrix representation, and linear combinations of the columns of the matrix are precisely the elements of the column space of the matrix. This shows that rho C of V is an element of the column space of the matrix representation. Now, all that remains for us to prove is that this restriction is an invertible linear transformation. It is automatically injective because it is a restriction of an injective function rho C. So the real question here is why it is surjective. To prove that it is surjective, let's take any vector y in the codomain of this linear transformation, and the codomain here is the column space of the matrix representation. Because y is a vector in the column space, it is equal to the matrix vector product of the matrix representation and some column vector x. The number of components in this vector x is the number of columns in the matrix, so this is equal to n, the dimension of the vector space U. Let V be the uncoordinatization of the vector y relative to the basis C, this is a vector in V, and let U be the uncoordinatization of the vector x relative to the basis B, this is a vector in the vector space U. I claim that the vector V is a member of the range of T. For this, let's compute what T does to the vector U. Vector U is rho B inverse of the vector x, And then we apply the fundamental theorem of matrix representation to the linear transformation T. We have row B composed with row B inverse in the middle. This composition is the identity linear transformation because they're inverses of each other, and the identity linear transformation doesn't change its input. Next, let's recall that the matrix vector product representation matrix times vector x is the vector y. And row C inverse of vector y is how we define vector v. So if you look at the beginning and the end of this computation, you will see that T of u is equal to v. This tells you that the vector v is equal to the value of the linear transformation T on some input u from the vector space u. Therefore, the vector v is a member of the range of the linear transformation T. Also, the vector v was obtained by uncoordinatizing the vector y relative to the basis C. Therefore, if we coordinatize the vector v relative to the basis C, we will get vector y. This shows that the restriction of row C to the range of T is surjective as a linear transformation from the range to the column space. Because every vector y from the column space of the matrix representation is equal to the value of row C on some input from the range of T. So this restriction is both injective and surjective as a linear transformation, therefore it is invertible, and this establishes the isomorphism between the range of T and the column space of the matrix representation. Let's see this result in action. We have this linear transformation T from the vector space of 2 by 3 matrices into the vector space of polynomials of degree at most 3. We fix nice bases B of matrices and C of polynomials, and this allows us to construct the matrix representation of T relative to these two bases. We have constructed this matrix representation in the last video, so I'm simply going to copy this result here. And now we will compute the column space of this matrix. For this, we obtain the reduced row echelon form of this matrix. We notice that columns 1, 2, 3, and 5 are the pivot columns. Therefore, the basis of the column space of this matrix consists of the columns 1, 2, 3, and 5 of the original matrix. But now we can use this basis of the column space to construct a basis for the range of the linear transformation. And to go from the column space back to the range, we need to uncoordinatize each of these column vectors relative to the basis C. When we do this, we obtain 4 polynomials in the vector space P3, and these polynomials form a basis of the range of T. Let's observe that there are 4 vectors in the basis of the range of T. This tells us that the dimension of the range is equal to 4, but this is the same as the dimension of the vector space P3, and range of T is a subspace of P3. A subspace of a vector space which has the same dimension as the vector space must be already equal to the entire vector space. Therefore, the range of T is equal to the entire vector space of polynomials of degree at most 3, and in particular, this tells us that T itself is a surjective linear transformation. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss matrix representations of invertible linear transformations. I will see you later.